Okay, I think we can start. Can you hear me? Okay, so let me share my screen. Okay, can you see the screen? Can you see the screen now? Okay, so for today's exercise class, we'll discuss a new topics, which is Feynman rules. And so in particle physics, we have two important quantities. First, for a decay process, we want to find the decay rate, which is related to the lifetime. And for a scattering process, we want to find the differential cross sections, which basically means how the outgoing particles distribute in a spherical surface. So to find these two quantities, we use the so-called Fermi-Golden rule. So this refers to the transition rate, and this will refer to the phase space, which is the density of states of your final states. And this is called amplitude, or the matrix element, which will be evaluated by the Feynman rules. And you may have seen this in your advanced quantum mechanics course, but here we don't derive it because it's very complicated. So we just use these two expressions. I just copy it from extra slides to find the decay rates and also the differential cross sections. So this is just a recap of what we are doing now. So let's go to the exercise questions. So So in this question, we use a simplified theory with 3 particles, A, B, C. So it is like this. And later in the course, we will consider the true Feynman diagrams, which you learn how to draw previously. But now we just use a simplified theory to demonstrate how to use the Feynman rules. So the first question, it asks us what conditions do the number of external lines should satisfy. So there are 2 approaches for these questions. And the first approach is to consider how to construct a diagram. And the idea is that any diagram can be constructed from the primitive vertex by 2 actions, which I call branching and merging. So let me draw. So first, we have a primitive vertex like this. And what branching means is that we can add more external lines like this. So we can extend the external lines. And by doing so, we can see that initially we have 1 A lines, 1 B lines, 1 C lines. But after I add a branch, this B will become an internal line, and meanwhile we have 1 more A line and 1 more C lines. So in general, when we do a branching action, the number of 1 kind of lines will decrease by 1, while the other 2 types of external lines, the number will increase by 1. So for example, if I draw 1 more branch here, then the number of C will decrease by 1, but meanwhile we have 1 more A and 1 more B. So what does it mean? So if we consider initially, we have 1 A line, 1 B line, 1 C line, and each time when I draw a new branch, 1 kind of line will decrease by 1, while the other will increase by 1. And you can see that the number of lines will always be all odd or all even. So is it clear here? So but up to now, we only consider the diagrams without the loops, right? Because I just add more external lines. But we also have to consider the case with the loops, which will be which can be constructed by the action of merging the lines. So, for example, we can once again start from this primitive vertex. And here you can see that we can merge this B and C to form a new vertex. So this is what merging means. And by merging 2 external lines, we can see that the number, also initially we have 1 A, 1 B, and 1 C. But after I merge this, the B and C will become internal lines. So the number will decrease by 1. But at the same time, there's a new A external line. So the number of A lines will increase by 1. So in general, when we merge two different kinds of external lines, there will be 2 types of lines which will decrease by 1, and the other type of line will increase by 1. So it still preserves the condition of all odd and all even. And we also have another case in which we can merge 2 lines of the same type. So for example, here, we can merge these 2 external A lines together to form a loop. And in this case, we can see that initially we have 2 A lines, but after merging them, they will become internalized. So the number will decrease by 2. While for the other kinds of lines, the number will remain unchanged. So in all these cases, you can see that the number of lines still preserve the condition of all odd and all even. Assuming initially odd. Yeah, because all the diagrams is constructed from this primitive vertex, right? So let me consider an example. So we can consider this. So how is this diagram constructed? So we can first start with a primitive vertex. And then we do the action of branching. And we do branching again. B, this B, this A, right? And then we do the action of merging. So you can see any diagrams can be constructed from the primitive vertex based on these 2 actions. And all these actions will preserve the odd or even condition. So the conclusion is that for all diagrams, the number of external lines will be all odd or all even, depending on the number of vertexes. So is it clear? So this is the first approach. And in your text, in the Griffith's textbook, we have the second approach, which is to consider cutting the internal lines and then rejoin them. So the idea is, so let me demonstrate this by an example. So let's consider this complicated diagram. So so first we cut all the internal lines. So and we form a new diagrams like this. So in these diagrams, we can see that so all these are external lines. All these are external lines. So in this diagram, NA will equals to NB equals to NC equals 4. And then we start to rejoin them. So for example, we can rejoin these two. And after we rejoin them, this will become an internalized. So every time when we rejoin, there will be one kind of lines, the number of decreased by 2. Right? So for example, when we rejoin these two, then the number of C lines will decrease by 2. And when we rejoin these two lines, the number of A lines will decrease by 2. And when we rejoin these two C lines, the C lines will decrease by 2. So you can see every time when we rejoin, we still preserve the all odd or all even condition. So this is another approach to this question. So we can move to the next part. So this question asks us to find the next two most likely decay modes of A. So for the next decay modes, we can consider add more branches to this. But this is not allowed because we have an A in the initial state and also an A in final state, which is kinematically forbidden. So we have to branch it again. So that's the one of the answers. P. And this is allowed because we assume the mass of B and C is much smaller than A. So it's kinematically allowed. And the next diagram, we can consider the branching of the C particles. But similarly, we have to make this A into internalized. So this will be A to C plus so this is the next two decay modes allowed by this simplified theory. Okay, so let's move on to the last part. So for the last question, we want to actually use the Feynman rules to calculate the amplitude. So first, we want to draw all the Feynman diagrams, the lowest order diagrams for this AA to AA process. But before that, I want to talk more on these two diagrams. So you may have seen this in your lectures. This is the process of 2A into 2B scattering. And when calculating the Feynman rules, we actually consider two diagrams like this. And you may wonder how these two diagrams differ from each other. And the answer is they have different connections of the external form momenta. That means the external particles interact by different internal paths. So we consider them as the different diagrams. And specifically, we can construct a table like this. So we can consider the connections between each two form momenta. So let's consider the first diagram here. So if we consider P1 and P2, so they are connected by these C lines. So I just write a C here. And then we consider P1, P3. So P1, P3 is here. So they are next to each other. So I just put a tick here to indicate that. And P1, P4, they are connected by the C. So just write C here. And so on, you can write down all the connections between each form momentum. And for the second diagrams, you can do the same thing. So for example, P1, P2, they are connected by the C lines. And P1, P3 is also connected by C, and so on. And you can see that these two diagrams have different connections from this table. So that's why we consider them a different diagrams. And if you draw something like so you can also draw something like this. This is a and you may ask if this diagram a new diagram, and you can do the same thing here. And you can write down all the connections. So here P1, P2 are connected by C, and P1, P3, they are next to each other, and P1, P4, they are connected by C, P2, P3, they are connected by C, and P2, P4, they are next to each other, and P3, P4, they are connected by C. So we can see that the connections of the form momentum is just the same as this diagram. So we do not consider this as a new diagrams because they have the same connections. So that's in general how we draw the diagrams, draw all the diagrams of a process. So we can back to this process, AA to AA. And so the first diagrams we can think of is like this. And similarly, let's write down the connections. So let's label this as P1. So let's label the four momentum like this. And similarly, we can construct a table to record the connections of this four momentum. So P1 and P2, they are connected by the C. So in general, we also have to consider these connections. Because the shape is symmetric, so we can just consider this C here. And P1, K1, they are connected by B. And P1, K2, they are connected by BC or CB. And to indicate this, I just put a cross here. And P2, K1, they are also just put a cross here. And P2, K2, they are connected by the B. And K1, K2, they are connected by C. So that's the connections of these diagrams. And for the next diagrams, we can consider the exchange of these two legs. So it's like this. And we can do the same thing here. And P1, P2 is C, P1, K1. So it's like this. So I just lay cross here. And P1, K2, they're connected by the B. And P2, K1, they're connected by B. P2, K2, just put a cross here. And K1, K2, they are connected by the C. So you can see that this diagram have a different connections from our first diagram. And similarly, we can exchange these two legs. And you can do it yourself to see to prove that the connection is indeed different from the previous two diagrams. And for the remaining three diagrams, we can exchange this, exchange the B and C to form the remaining three diagrams. So in total, we have 6 diagrams. So you may ask whether this will be a new diagram, but you can check you can check that the connection of the form momentum is in fact same as one of these diagrams. So in total, we only have 6 independent different diagrams. So that's the answer for part 1. So next, we want to use these 6 diagrams to calculate the probability amplitude. And we can first consider this diagram. So we just write down, label all the external form momentum and also the internal form momentum. And it doesn't matter whether you draw it to right or to left. The directions doesn't matter as long as you follow the Feynman rules. So the first step is to write down all the vertex vectors. So for each vertex, we write down a vector of minus ig. So here we have 4 vertices. So we just write down a vector of minus ig to the power of 4. And as you remember, previously we say if a diagrams have more vertex, it will be more suppressed. And the reason is because in Feynman rules, each vertex will have a vector of minus ig, and g is smaller than 1. So the more vertex, the more suppressed is the diagram. So the next step is to write down the propagators. So for each internal line, write down vectors. And here we assume B and C are massless. So we just have to multiply 4 such vectors. And the next step is to consider the energy momentum conservation at each vertex. So so the final expression is like this. So we can first consider this vertex. So we have Q1 in, P2 in, and Q2 out. So it's P2 plus Q1 minus Q2. And for the second vertex, so we have Q2 in and K1 out, Q3 out. So it's Q2 minus K1 minus Q3. And similarly, you can work out the factors for the remaining 2 vertices. And the next step is to do the integration over the Q here. So we just add these 4 factors and do an integration. So after simplifying the 2 pi factors, so the integration is like this. So now let's do the integration. And we can first consider Q4. So for Q4, we can consider this delta function. So it's the same as Q4 minus P1 plus Q1. So we can just replace all Q4 by P1 plus Q1. So here, it's P, oh, hey, such was something. It's Q4 minus Q1 minus P1. Yeah, so we just replace all Q4 by Q1 minus P1. So we have Q4 and Q4 here, and we just have to replace them by Q1 minus P1. Yeah, and similarly, we can do the integration on Q3. So Q3, we can consider this delta function. So we just have to replace all the Q3 by Q2 minus K1. And similarly, we can do the integration on Q2 and just replace all the Q2 by P2 plus Q1. And you can see that this 2Q1 will cancel. And finally, we'll left with such integrations. And here I just multiply a 2 pi and divided by 2 pi here. Because in the last step, we will cancel this factor and multiply an I. So finally, for this diagram, the amplitude will be like this. But this is just one diagram. And in previous question, we have found 6 diagrams. So we have to calculate the amplitude for all of them and then add them up. So for this diagram, we have this amplitude. And we have the second diagram like this. But this diagram can is just exchanging the K1 and K2. So we can just replace all the K1 into K2. So we can just replace this K1 by the K2. And for this diagram, we can see that this is just exchanging P2 and K1. So we can just replace all P2 by K1 and replace the, okay, here P2 replace to K1 and also K1 replace to P2. And we also have three diagrams, which is exchanging the B and C. But in this question, we assume B and C are massless, so they will have the same propagators, and so the amplitude is just the same at these three diagrams. So we just have to multiply each amplitude by 2. And so when we add them up, the final full amplitude will be like this. And we can just leave the integration here because it's too complicated to evaluate. So this is the answer for the last question. Do we assume all QI to be the same? What do you mean QI here? So previously, we do not consider QI to be the same, right? Because we label them as Q1, Q2, and Q3, Q4. But after we do the integrations, we will just live with a Q1, and this is in fact a definite integrals from minus infinity to from 0 to infinity. So so it's just a dummy variable. So I just drop the Q1 into Q. So this is just a number. So here it's the same everywhere. Oh, sorry. Yeah, it should be a integration on 4 momentum. So it can add back the 4 here. Yeah. Yeah, if you want to do this integration, you have to use something like spherical coordinates to break down this D4Q. Yeah, so it's very complicated, so we don't evaluate it here. So that's all of the exercise class. And if you have no questions, you can leave. And if you have any question, you can raise here. Okay, goodbye. Okay, see you next week. But how?